Welcome to our discussion on dynamic panel data model, and today what we are going to discuss is one step versus two step GMM estimation. These are important models, so let us learn little more on one step versus two step GMM. So this is dynamic panel data model. So this is one step versus two step. Two-step GMM. And today's discussion is based on this important reference given by Frank Windmeiser, and the title is a finite sample correction for the variance of linear efficient two-step GMM estimators. This is the reference this is the title of the paper by Frank Windmeiser, Windmeiser. So let us consider, this is the reference, let us consider the following econometric model. Following panel data model. Wherein YIT equals to beta 0 XIT plus AI plus VIT, and this is UIT, this is VIT, and AIT plus VIT equals to UIT. And then what we assume that I is basically 1 to n and T equals to 1 to capital T, and XIT is correlated with the past values, okay, is correlated with the AI, but predetermined, this is very important, predetermined with VIT. What does it mean? It means that this implies expectation of XIT and VIT plus S equals to 0 for s equals to 0, then 1 t minus t. Now, if we put s equals to 0, that means expectation of xit and vit is also 0. So, xit is not correlated with the present error term, right, but expectation of xit and vit minus r not equals to 0, where r equals to 1 to t minus 1. Now, if we put r equals to 1, it means expectation of xit and vit minus 1 is not equals to 0. So, essentially it says the explanatory variable is correlated with the past error, but not the present, okay, and future. That is why it is called predetermined. Okay. And in case if we combine these two and both are not equals to 0 type, then that is a situation of endogeneity, wherein the explanatory variable is correlated with the present as well as the past error, and if neither of them is non-zero, that means in presence of expectation xit vit plus 1 is 0, expectation xit vit minus r, that is also 0, that is a situation called exogeneity, strict exogeneity, right. So, that means in a variable which is strictly exogenous, it does not depend on the error in past, present and future, that is all. That is called strictly exogenous variable, a variable, explanatory variable, which is not at all correlated with the past, present and future error. When it is predetermined, it is not related with the present, but it is related with the past, that is called predetermined, right. And endogenous variable is related with the present as well as the past. That is the difference between predetermined, endogenous and exogenous variable. So, if that is the case, if you recall, we started our discussion of dynamic panel data model assuming that we have a right hand side explanatory variable which is not strictly exogenous. That means it is predetermined or endogenous, right. So, if that is the case, in place of xit you can very well assume yit minus 1. Okay. Then Arellano and Bond (1991), Arellano and Bond 1991 estimator is basically GMM estimator, in the first difference that we have already discussed in the first difference. So, what we did basically, delta yit equals to beta 0 delta xit plus delta uit, okay, and t equals to 2 to capital T, right. So, how many moment condition? With t into t minus 1 divided by 2 sequential instrument. Okay, t into t minus 1 by 2 sequential estimates instruments that we are using. And then if you recall our Z matrix, that means the instrument matrix was this xi1 and then 0 xi1 xi2 and then what we have is like this 0 0 0 and then xi1 and xi t minus 1. So, that was our instrument matrix we assume, and moment conditions are given by expectation. What was the moment condition? Expectation of Z I prime delta u I equals to 0. That means the instruments are not correlated with the differenced error structure, right. That was the moment condition where delta ui equals to actually t minus 1 vector of this delta ui2 delta ui3 delta ui t and its transpose, right. In this setup, a one-step GMM estimator, is given by the following: beta 1 hat equals to delta x prime z into w in inverse z prime delta x and then whole inverse delta x prime z w in inverse z prime delta, sorry, this is delta y, okay, delta x prime z w n inverse z prime delta y. This is the one step GMM estimator, right. And then what is delta here? Wn inverse, this is an important element in this GMM estimator which we need to pay special attention to. This Wn inverse is basically, it is an weight matrix. Where is it coming from? Basically an initial positive definite weight matrix, okay. weight matrix. For example, 2 SLS, 2 stage least square sets Wn equals to 1 by n z prime z, okay. And initial weight matrix that is efficient when VIT R I D is basically Wn equals to 1 by n sum of Zi prime h and Zi I running from 1 to n. Now, what is this h over here? H is basically h equals to this. This is very interesting. H is 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. So, that means 2 is there on the diagonal element, and then these are all 0 and this is also 0 and this is again 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. This is basically the h. Now, how do you get the 2-step GMM? 2-step GMM is beta 2 hat rather equals to what I am doing, delta x inverse z w in inverse, then I am using beta 1 hat estimated earlier and then z prime delta x whole inverse, then delta x inverse z w in inverse beta 1 hat z prime delta y. If you compare the beta 2 hat and beta 1 hat, everything else is same, only thing is that while estimating beta 2 hat, I am incorporating this beta 1 hat estimated earlier. That is why it is called 2-step GMM, right. Now, why do we need this 2-step GMM? To gain on the consistency front. So, 2-step GMM is more consistent than the 1-step GMM, but in the estimation of 2-step GMM, since we are using beta 1 hat estimated through the first step, as a result of which estimated asymptotic standard errors of beta 2 hat, it is still efficient, but the standard errors are severely downward biased. That is the problem. So, to gain consistency, what we are losing is basically efficiency. That means the standard errors are actually downward bias. We are getting a bias in the standard errors of this beta 2 hat. So, what is happening? The estimated asymptotic standard error, estimated asymptotic standard errors of the efficient two-step GMM estimator can be severely downward bias. Severely downward bias. Okay, severely downward biased. In small samples. And this bias is severe enough to make two-step GMM estimator useless for inference making. This is told by Arellano and Bond, 1991. Okay. So, what is happening here compared to one-step GMM estimator? Two-step GMM estimators are more consistent, but to achieve consistency, what we are losing here is we are getting a downward bias in the asymptotic standard error of this two-step GMM estimators. So, asymptotic standard errors of the efficient two-step GMM estimators are severely downward bias, and the bias is enough to make it useless for inference making, as pointed out by Arellano and Bond. If that is the case, then what is required is to correct this downward bias of the two-step GMM estimator. So, that is made by Windmeyer 2005, and that we can implement in Stata by a simple robust command. So, what is required is correction of this downward bias of the two-step GMM, downward bias of the standard errors of the standard errors of two-step GMM estimators. And that is done by Weinmeier 2005 by the robust command. Okay. So, that is what I wanted to tell you, that there are two types of basically GMM estimator, both in the context of difference as well as in system. We can get two types, either one step or two step. And actually, if the difference between one step and two step is basically on a particular weight matrix. If you look at, the difference is the in the way we are estimating this, in one step everything is same. One step is this is the one step, and in two step we are using the beta 1 hat estimated in the first step, and then we are using it here. So, just because beta 1 hat is used here, so this is making two step GMM estimator consistent, more consistent than the first step, but the cost is actually in terms of the downward bias that we are getting in the asymptotic standard error of beta 2 hat, which should be corrected by the Weinmeier correction. Okay. So, that is why two-step GMM estimators are preferable compared to one step because of this consistency gain, but this is the cost. That is why some researchers, they prefer to report both one step as well as two step GMM estimator to show how much bias we are getting in the standard error of beta 1 hat, and then we try to implement that Weinmeier correction to correct for that downward bias.